Good evening everyone, good evening. I welcome you all again to JEE Enthuse. I hope you guys are doing great, having a good time. Well people, first of all, just let me know in the chat box if I'm audible and visible to everyone. Just let me know in the chat box if I'm audible and visible to everyone. Hello Ishpreet, hello Ashwarya. Hi Zoner, hello Saja, hi Dipanshi. Hello Ashwarya, hi Krishna. Welcome back everyone, welcome back. Good evening. Yeah, we are meeting after so long, right? Just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys properly. Good evening Lakshmi. Hello Gangotri. Hello Sugana, hi Ritu. Hello Nandini. Welcome back. Hello Harshit, good evening everyone, good evening. Perfect. So as you all must be knowing, from tonight we are going to resume the JEE 2023 batch, right? I'm going to do that from tonight itself, as well as JEE 2022 batch, right? We are done with the JEE 2021. Okay, so from now onwards, it's going to be your turn, right, to kill the course right here on the JEE Enthuse with me. Okay, so people, till now in the atomic structure, I think we are done with the Bohr's model, right? Bohr's model we did in the last session of atomic structure. And in the tonight's session, we are going to cover these three topics. One is going to be your hydrogen spectrum. Then we'll be talking about the de Broglie's hypothesis. And at the end, we'll be covering the Heisenberg's uncertainty principle as well. These are the three important topics which we are going to cover right here in the tonight's discussion. Okay. So before starting the session, the ones who are new to the channel, let me introduce myself. Well, people, my name is Wassim and I'm your chemistry master teacher right here on this JEE Enthuse channel. Yeah. The ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this JEE Enthuse channel. Yeah. So do like the video, share the video with your friends, and do subscribe to the channel as well. Okay. No, Dipanshi, this is not going to be the mentee. This is going to be the normal session in which I'll be teaching you basically, right? It's not going to be the mentee. Okay. Alright, so people, you can let me know in the chat box if you guys are super duper excited about the tonight's session as well. Yes, Zoner, I'll be doing that. I'll be doing that, yes. Just let me know in the chat box if you people are super duper excited about the tonight's session as well. Let me see the josh of the session, then only we'll be starting the tonight's session with something called as hydrogen spectrum, right? Yes? Perfect guys, perfect. Alright, so let's get going with something called as hydrogen spectrum, right? Before talking about the hydrogen spectrum, let me give the quick overview of certain things which we have discussed in the last session, right? People, in the last session of atomic structure, I gave you certain formula to calculate the radius of the nth Bohr's orbit, velocity of the electron in the nth Bohr's orbit. We talked about something called as total energy of the electron in the nth Bohr's orbit, potential energy, kinetic energy, all those things were done in the last session, right? And if you remember, as per your Bohr theory is concerned, right, total energy of the electron in the nth Bohr's orbit is given by the formula minus 13.6 Z square divided by n square electron volts, and this formula is only valid for single electron species. It is only valid for single electron species. This is something which we have discussed in the last session. I have given you the derivation of this formula as well, if you remember. Okay, right? And there were a few important points which I told you in the last session. What were those important points? I told you when the electron makes a transition from lower energy state to higher energy state, it absorbs energy, which will be exactly equal to the difference in the respective energy shells, right? Whenever the electron makes a transition from low energy state to higher energy state, it absorbs energy equal to the energy gap between the two shells, right? Okay. And similarly, when the electron makes a transition from higher energy state to lower energy state, it emits energy in the form of radiations, right? Okay. And that energy emitted by the electron is again equal to the energy gap between the two shells in which the electron is making the transition of. Yeah, that's something which we have discussed in the last session. Okay, So people, let's get going. Let's get started with something called as hydrogen spectrum. I'm sure you would have studied something called as Lyman series, Balmer series, Paschen, bracket fund. Let's talk about those series one by one for the hydrogen atom, right? So let's say, let me draw a figure over here. Have a look. Let's say I've got the hydrogen atom first of all. Let's say I've got the hydrogen atom, which is the single electron species. It contains only one electron in it, right? Let's say this line represents the ground state of hydrogen atom. Wait just a second, it's not a straight line. Just a second, people. Let's say it represents the ground state of hydrogen atom. That means it represents the first energy state. Ground state, for example, n is equal to 1. Let's assume this is shell number 2, n is equal to 2 for hydrogen. Let's assume this is n is equal to 3 for hydrogen, right? Similarly, let's say this is n is equal to 4 for hydrogen, right? And as I keep on going up, the difference in the energy gap will be coming closer. These shells will be coming closer as I move far from the nucleus, okay? That's something which I'll be telling you in some time, right? Let's say this is one more shell, which is n is equal to 5, right? And let's assume this is one more shell, which is n is equal to 6. And over here somewhere, there is n is equal to infinity. N is equal to infinity, right? Okay. Now, as I told you in the last session of the Bohr's atomic theory, when the electron makes a transition from lower energy state to higher energy state, it absorbs energy. And similarly, when the electron makes a transition from higher energy state to lower energy state, it emits energy, right? Okay. Now we will understand a few important things. For example, I have got the electron in the hydrogen atom currently in the ground state. This is the electron currently in the ground state of hydrogen atom, right? Let's say I'm supplying some energy towards this electron. What is going to happen? This electron will excite. It will go into the higher energy states, right? Depending on how much energy I'm providing to this electron, right? Let's assume I'm providing some energy to this electron. It will definitely excite, right? It will go into some higher energy states. Let me tell you, the electron in higher energy state, it is very, very unstable. The electron in the higher energy state resides there for just 10 raised power minus 8 seconds. The electron, when present in higher energy state, is considered to be unstable, right? It just resides there for 10 raised power minus 8 seconds, due to which the same electron, which was earlier in the ground state, after the absorption of energy, it went to the higher energy state, right? And it just resides in the higher energy state for 10 raised power minus 8 seconds, due to which the same electron again makes a transition to the lower energy states, right? And when the electron makes a transition from higher energy state to lower energy state, it emits energy in the form of radiation, right? It emits energy in the form of radiation, okay? That's something which I assume all of you must be knowing now, yeah? Now people understand a few important things. See, this was the electron at ground state. I gave some energy to this electron. It went to the higher energy state, right? In the higher energy state, electron is highly unstable. Now it will again make a transition from higher energy state to lower energy state. And remember, when the electron makes a transition from higher energy states to shell number 1, when the electron makes a transition from higher energy states to shell number 1, we get a series of spectral lines. We get a spectral lines over here. And this set of spectral lines which I get over here, when the electron makes a transition from higher energy state to shell number 1, right? This series of lines is something which we call as Lyman series. This is something which we call as Lyman series. When the electron makes a transition from higher energy state to, I'm writing it over, higher energy state, which I'm representing by N2, to shell number 1, right? Okay. Similarly, when the electron makes a transition from higher energy state to shell number 2, we get a series of spectral lines over here, right? And this series of spectral lines is something which we call as Balmer series. So Balmer series is obtained when the electron makes a transition from higher energy state, which I'm representing by N2, to shell number 2. Similarly, when the electron makes a transition from higher energy state to shell number 3, we again get a series of lines over here. And this series of lines, this series of spectral lines which we get is something which we call as Paschen series. And in the Paschen series, the electron makes a transition from higher energy state N2 to shell number 3. In the similar way, we have got other series as well. From higher energy state to shell number 3, we get something. This was Lyman, Balmer, Paschen. Now it's going to be bracket series. This is something which I call as bracket series. in which electron makes a transition from higher energy state N2 to shell number 4, right? Similarly, when the electron makes a transition from higher energy state to shell number, just a second, 1, this was 2, this was, okay, this was bracket, okay, it's not going to be this, just a second. The electron, when it makes a transition from higher energy state to shell number 5, we get again a series of lines called as Fund series. And in the Fund series, the electron makes a transition from higher energy state to shell number 5, correct? And similarly, we have got one more series when the electron makes a transition from higher to shell number 6, we call that as Humphrey series as well, okay? So these are the different series which we get when the electron makes a transition from higher energy state to shell number 1. That series is called as Lyman series. Then we have got Balmer series, Paschen, right? Bracket, Fund, and so on, yeah? Right? Okay, someone is saying why energy is negative. This negative sign has a significance. That's something which I've discussed in the last session. I think you are new to the session. This negative sign simply tells you that the electron is under the influence of the nucleus. This negative sign, it simply gives you the idea about the fact that the electron is under the influence of the nucleus. See, if you look at the infinite energy state, this n is equal to infinity. When the electron is present at n is equal to infinity, okay, its energy is taken to be 0. Its energy is to be taken as 0. That means the electron right now, when present at the infinite energy state, it is not under the influence of the nucleus, right? And when the electron comes closer, it comes under the influence of the nucleus. That's why energy of the electron keeps on getting negative, right? I'm sure it's clear to you, okay? Right, people? Now, there are few terminologies which you need to take a note of. What are those terminologies? Those are really, really important. See guys, have a look properly. If I look at the Lyman series clearly, the electron makes a transition from higher energy state to shell number 1. Okay, have a look properly, guys. See, this line in the Lyman series from 2 to 1, this is something which we call as first line of Lyman series, or we call it as H alpha line. We call it as a H alpha line of Lyman series. The first line of Lyman series, when the electron makes a transition from 2 to 1, is what we call as first line of Lyman series, or we call it as H alpha line of Lyman series as well. Similarly, when the electron makes a transition from 3 to 1, this is what we call as second line of Lyman series, or you call it as H beta line of Lyman series, right? Similarly, when the electron makes a transition from 3 to 1, right? When the electron makes a transition from, 4 to 1, this line is called as the third line of Lyman series, or you call it as, this was alpha, this is beta, now it's going to be H gamma line of Lyman series, right? Similarly, people, if you look at your Balmer series right here, this is the first line of Balmer series, or you call it as H alpha line of Balmer series. This is the second line of Balmer series, you call it as H beta line of Balmer series, and this is what you call as H gamma and so on, third line of Lyman series, third line of Balmer series, right? Okay, similarly, you can designate all the other lines as well, right? This is what we call as H alpha, or first line of Paschen. This is second line of Paschen, H beta. This is H gamma, right? And so on. I want you guys to remember these terminologies very, very, very well. Okay, I'm sure you would have noted this down. Right? Now, people, understand few important things. See, for example, if I talk about the first line of Lyman series, that means when the electron is making a transition from 2 to 1, higher energy state to lower energy state, it will be emitting energy, right? It will be emitting energy in the form of radiation. That radiation is definitely going to have some wavelength. Now, how do we calculate the wavelength of the radiation which is emitted when the electron makes a transition from higher energy state to lower energy state, right? That is the point. Let me tell you how to calculate the wavelength of the radiation emitted, wavelength of the photon emitted when the electron makes a transition from higher to lower energy state, right? Let me tell you that right now, okay? I'm going to erase this part. I'm sure you have noted this down properly, okay? First of all, let me tell you there is a formula called as Rydberg's formula. There is something called as Rydberg's formula, and this Rydberg's formula, which I'm going to show you right now, it is used to calculate the wavelength of the radiation of the radiation emitted or absorbed when electron makes a transition. When electron makes a transition, right? And what is this formula all about? What is this formula all about? Have a look properly, guys. I'm writing something like this. This symbol represents something called as wave number. This symbol right now, it represents something called as wave number. What is wave number all about? Wave number is nothing, that is inverse of wavelength, 1 divided by lambda. As per Rydberg's formula, it's equal to R Z square 1 upon N1 square minus 1 upon N2 square. Right? Be careful with the terminologies, people. Be careful with the terminologies. N1 over here. N1 represents the lower energy state. N2, it represents the higher energy state. It represents the higher energy state. This R is something which we call as Rydberg's constant, and Z is the atomic number of the single electron species. Okay? And remember one more thing. You're not supposed to remember the value of R or something like that. No. Just remember one thing. Just remember one thing. Always in the questions, you are going to take the value of 1 by R as 911.5 angstroms. And as you all must be knowing, 1 angstrom is nothing, that's 10 raised power minus 10 meters, right? 1 by R value, which is basically equal to 911.5 angstroms. This is something which you are going to take in the equations, right? This is the relation, which is something which we call as Rydberg's formula. It is used to calculate the wavelength of the radiation emitted when the electron makes a transition from higher energy state to lower energy state, or the same formula is used to calculate the wavelength of the radiation absorbed when the electron makes a transition from lower energy state to higher energy state, right? Okay, I'm sure it's clear till here. Yeah? Okay? Right? Now people understand few important things. I'm sure this is clear to everyone, right? Now I'm going to show its usage in some time. Let me tell you the Z over here. This is atomic number of the single electron species over here, right? If I'm talking about hydrogen, Z value is going to be 1. Yeah? Okay? Perfect. Umar, on NEET Elite for 2023 students, I'll be taking session on, right after Sunday, because Sunday there is NEET examination, so Sunday I'll be doing the paper discussion. From Monday, I'll be giving you continuous lectures for NEET 2023 students and as well as 2022 students on NEET Elite channel, yeah? Okay, so I'm sure everything is clear till here, right? Now people, there's something which I've told you, the electron in the hydrogen atom, when gets excited to the higher energy level, stays there for 10 raised power minus 8 seconds, falls back to the ground state, during which it emits radiation of different wavelengths, which are obtained as colored lines on the photographic plate, right? Okay, and this is something which I've told you in detail, right people? Now there are few terminologies. There are few terminologies which you need to remember. What are those terminologies? See guys, the first thing, I'm starting with something as Lyman series. And Lyman series, as I told you, when the electron makes a transition from higher energy state, which is N2, to lower energy state, that is going to be N1, which is 1 in case of the Lyman series, right? In case of the Lyman series, correct? If I talk about the first line of Lyman series, or I told you this is called as H alpha line of Lyman as well. What is H alpha? H alpha for Lyman, it is the first line of Lyman, when the electron makes a transition from 2 to 1, right? So currently the electron is making a transition from shell number 2 to shell number 1, right? As I told you, lower energy state is represented with N1, higher energy state is represented with N2, right? N2 value is 2 in this case, N1 value is 1 in this case. And which atom am I talking about? I'm currently talking about hydrogen atom, right? Right? Okay. Now we will have a look properly what I'm going to say now. Okay, the electron is making a transition from 2 to 1 in case of H alpha line, okay? In case of first line of Lyman series. And when the electron will be making a transition from 2 to 1, higher energy state to lower energy state, it will be emitting radiation. What is going to be the wavelength of that radiation emitted? That is something which I'll be calculating by using Rydberg's formula, right? I'll clearly say 1 divided by lambda alpha. 1 divided by lambda alpha is equal to, it's going to be R Z square. Z value for hydrogen is 1, so 1 ka square comes out to be 1. 1 upon N1 square minus 1 upon N2 square. 2 to 4, correct? So from here, can I calculate the wavelength of the radiation emitted during the first line of Lyman series? Absolutely. So you'll be getting 1 divided by lambda is equal, it's going to be r, it's going to be 4 minus 1, that's going to be 3 divided by 4. From here, if you take the reciprocal of this thing, if you take a reciprocal of this equation, you'll be getting something like this. Lambda alpha is equal to 4 divided by 3r. And already I've told you 1 divided by r. Already I've told you 1 divided by r is nothing, that's 911.5 angstroms. So it's going to be 4 divided by 3 multiplied by 911.5 angstroms. So people, let me tell you, this is the wavelength of the radiation emitted in case of hydrogen atom when the electron makes a transition from 2 to 1, right? This is the wavelength of the energy of the radiation emitted during the first line of Lyman series. I'm sure it's clear to everyone, right? Yes? Perfect? Absolutely. Yes, Saja, are we resuming that as well? Just wait for it. Just wait for like 1 or 2 days, right? Just wait for it. I'm going to resume all the series which I had started long back. Nikita, no, not yet, not yet. All right, so I'm sure this is clear to everyone. This was the first line of Lyman series, the wavelength emitted during the first line. Similarly, let's assume I'm talking about the second line of Lyman series, right? Second line of Lyman series means the electron is making a transition from shell number 3 to shell number 1. Yeah? Okay, that's something which I'll be calling as the second line of Lyman series or H beta line of Lyman series, right? What is going to be the wavelength emitted in this case? You'll be simply writing 1 divided by lambda beta is equal to r, z value is 1, 1 ka square is 1, divided by n1 square minus n2 square, 3 3s are 9. So the value from here, you'll be getting something like this, 1 divided by lambda beta is going to be equal to r multiplied by 9 minus 1 comes out to be 8, 8 divided by 9, correct? Or if you take reciprocal, you'll be getting lambda beta is going to be equal to 9 divided by 8 multiplied by r, or you can write 1 by r separately, and 1 by r value, few minutes back I told you, that's nothing, that is 911.5 angstroms. So people, you just need to calculate this value. Okay, this is going to give you the wavelength of the radiation emitted during the beta line of Lyman series, during the transition of 3 to 1 in case of the Lyman series. I'm sure it's again clear to everyone, right? Okay, perfect. Yes, okay. Moving on people, have a look. There is something called as, just a second. There is something called as shortest wavelength or series limit in case of Lyman series. Okay, there is something called as shortest wavelength or series limit in case of Lyman series. What is that shortest wavelength or series limit? See, we know when the electron makes a transition from higher energy state to lower energy state, right? For example, the electron is making a transition from here to here. Okay, so it will be emitting energy. How much energy it will be emitting? Whatever is going to be the energy gap between these two shells, that's something which I'm representing by delta E. Okay, whatever is going to be the energy gap between these two shells, same amount of energy this electron will be emitting, where it will be making a transition from this energy state to this energy state, right? Okay, and this much amount of energy the electron will be emitting in the form of radiation, right? So it is basically equal to hc divided by lambda. That's something which you all must be knowing. This is something which we have discussed in the Bohr theory as well. Okay, now people understand. I'm talking about something called as series limit. I'm talking about something called as shortest wavelength emitted. When will be the wavelength emitted the shortest in case of Lyman series? See, the formula which I gave you right now, that is energy gap is equal to hc divided by lambda, right? Delta is equal to hc divided by lambda, correct? For the wavelength emitted by the electron to be minimum, delta E has to be maximum, energy gap has to be maximum. When is the energy gap maximum in case of Lyman series? When the electron makes a transition from infinity to shell number 1. I hope you are getting this properly. I'm talking about the shortest wavelength. I'm talking about something called a series limit, right? The wavelength emitted will be the minimum when the energy gap between the two shells will be maximum. And in case of Lyman series, when is the energy gap between the shells maximum? When the electron makes a transition from infinity to shell number 1, right? Yes? Yes, Aman, that will be done too. Just wait for it, that will be done too. Okay? Now people have a look. So let's get to know the lambda minimum over here. Again, I'll be using the Rydberg's formula. I'll say 1 divided by lambda minimum is equal to R Z square. For hydrogen, Z is 1 upon N1 square minus 1 upon N2 square, right? 1 upon N2 square. So the value over here, it simply comes out to be 1 divided by lambda minimum is equal to, it's going to be R, right? If you take reciprocal, you get lambda minimum as 1 divided by R, and 1 divided by R, already I've told you, it's nothing, it's 911.5 angstroms. So this is the minimum wavelength emitted by the electron when it makes a transition from infinity to shell number 1. This is the minimum wavelength which will be emitted in case of Lyman series, right? Yeah? Absolutely perfect. Right, people? This is the minimum wavelength emitted. Now, if I talk about the maximum wavelength emitted in case of Lyman series, if the question is asked, calculate the maximum wavelength of the radiation emitted. How do I do that? How do I do that? How do I calculate the maximum wavelength emitted in case of what? In case of Lyman series. For the wavelength emitted to be maximum, we know delta E is equal to hc divided by lambda. For the wavelength to be maximum, delta E must be minimum. Delta E must be minimum, right? Energy gap must be minimum. And in case of Lyman series, which energy gap is minimum? When the electron makes a transition from shell number 2 to shell number 1. Right? Use the Rydberg's formula, calculate the wavelength. That's it. Right? Right, people? So I'll be simply using 1 divided by lambda maximum will be equal to, this is going to be R, Z value is 1 upon N1 square minus 1 upon N2 square. The value is going to come as 1 divided by lambda maximum will be equal to R, it's going to be 4 minus 1, that's 3 divided by 4. Or if you take a reciprocal on both the sides, you get lambda maximum as 4 divided by 3 multiplied by 1 by R, and it's going to come as 4 by 3 multiplied by 1 by R is nothing, that's 911.5 angstroms. So this is the maximum wavelength emitted in case of Lyman series. I'm sure it's clear to everyone. So all these terminologies which were there in the Lyman series, I've discussed it one by one. Okay. Now, people, similarly, if I talk about something called as Balmer series, if I talk about the first line of Balmer series, the series limit of Balmer series, the maximum wavelength emitted in case of Balmer series, we can do that too, right? I'm sure you got the concept, yeah? Right? Clear? Clear to everyone? Okay. So let's get started with the Balmer series right here only. I'm starting with Balmer series. Right? First of all, let's try to calculate the wavelength emitted in the first line of Balmer series. I'm talking about the first line of Balmer series. First line of Balmer series means H alpha line of Balmer series. When do we get H alpha line in Balmer series? When the electron makes a transition from shell number 3 to shell number 2, right? When the electron makes a transition from shell number 3 to shell number 2, we get a line which is something which we call as H alpha line in case of what? In case of the Balmer series, right? N2 value you have, N1 value you have, use the Rydberg's formula, get the wavelength emitted, right? So from when the electron makes a transition from 3 to 2, what is going to be the wavelength emitted? Again, you are going to use the Rydberg's formula, 1 divided by lambda is equal to R, Z square is nothing, 1 divided by N1 square minus 1 upon N2 square. So the value comes out be 1 divided by lambda, this is alpha, 1 divided by lambda alpha is equal to R, 9 minus 4 comes out to be 5, 5 divided by 36, right? If you take reciprocal, you'll be getting lambda alpha over here as 36 divided by 5 multiplied by 1 divided by R. And as I told you already, this 1 by R is nothing, this is 911.5 angstroms. So this is basically the wavelength of the radiation emitted during the first line of Balmer series, when the electron makes a transition from 3 to 2. I'm sure it's clear to everyone, yeah? Right? Similarly, if I talk about the series limit of Balmer series, if you talk about something called as series limit of Balmer series, series limit means shortest wavelength. Shortest wavelength emitted in case of Balmer series. Okay. First of all, you all must be familiar with the fact delta E is nothing, that is hc divided by lambda. In case of Balmer series, I need to calculate the minimum shortest wavelength. For the wavelength to be shortest, delta E has to be maximum, energy gap has to be maximum. And in case of Balmer series, when is the energy gap maximum? When the electron makes a transition from infinity to shell number 2, right? This is the maximum energy gap in case of the Balmer series, right? So when the electron makes a transition from infinity to shell number 2, the radiation which will be emitted, its wavelength will be the minimum, and that minimum wavelength is something which I'll be calling as the series limit, right? Right, people? Yes, Abdul Aziz, tomorrow on NEET Elite, I'm going to take a session for 10 hours, right? We are going to do some 1,000 questions tomorrow. The session will start at 9 a.m. in the morning, yeah? Do it in that. It's going to be highly beneficial, okay? Yeah, perfect. So people, let's calculate the lambda minimum over here. Again, use the Rydberg's formula. I'll be calculating lambda minimum, 1 divided by lambda minimum is equal to R, Z square, that's going to be 1 upon N1 square, N1 is 2, 2s are 4, minus 1 upon N2 square, which comes out to be infinity only, yeah? So 1 divided by lambda minimum, in case of Balmer series, is going to be R divided by 4, correct? Or take the reciprocal, get the lambda minimum from here, it's going to be equal to 4 multiplied by 1 by R, and 1 by R value, that's something which I've told you, that's 911.5 angstroms, right? Okay? Correct, people? Yeah? I'm sure it's clear to everyone. So this is how you calculate the minimum wavelength, right? Yes, Krishna, shortest wavelength means series limit. Yeah? Shortest wavelength means series limit. Okay, I'm sure every single thing is clear till here, right? We talked about something called as, I showed you exactly how to calculate the shortest wavelength and the longest wavelength in case of different series. Similarly, you can calculate series limit of Paschen, bracket, and so on by using the Rydberg's formula. That's it, yeah? Okay, now we will understand. See, if I talk about Lyman series, the electron makes a transition from higher energy states to shell number 1, okay? When the electron makes a transition from higher energy states to shell number 1, electron will be emitting some different types of radiations, some different radiations it will be emitting, right? Those different radiations emitted by the electron, when it makes a transition from higher energy state to shell number 1, those radiations will be definitely having some different wavelengths, okay? Based on those wavelengths emitted by the electron, when it makes a transition from high energy state to shell number 1, we get a series of lines, Lyman series, and Lyman series, it falls into ultraviolet region. It falls into ultraviolet region. Similarly, Balmer series, it falls into visible region, right? Paschen series, it falls into the infrared. Bracket, again it falls into infra. Fund, it falls into far infra. And Humphrey, it falls again into far infra series, right? Okay, so if I'll ask you something like this. The electron is making a transition from 5th energy state to shell number 1 in case of hydrogen atom, right? Okay. The radiation which will be emitted, it falls under which category? You will clearly say it falls under ultraviolet, right? It falls under ultraviolet. 5th to 1, low energy state is shell number 1. That means Lyman series it's going to be. And Lyman series, all the lines in the Lyman falls into ultraviolet region. Yeah? I'm sure it is again clear to you. So remember it like this. UVIIFF, right? UVIIFF. That's how you're going to remember it. Or instead of far infra, you can write this as infra only. Okay, no need to write this far, right? Just infra only. That's it. Yeah? Okay, just tell me, you guys let me know in the chat box. The electron is making a transition from 5th energy state to shell number 3. The radiation which will be emitted falls under which category? The radiation which will be emitted falls under which category? Just tell me fast in the chat box. Then only I'll get to know whether you got it or not. See, from higher energy state to shell number 3. Higher energy state to shell number 3. That means Paschen falls under infra, right? Yes, perfect. Absolutely, guys. Absolutely. These are some questions which I'll come up with, and I'm sure you can all kill these questions. Well, all these questions I think we have done. The first 2 parts are already done, right? The first 2 parts are already done. Okay, now let's try to solve this one. Calculate the wavelength of lambda beta. Basically, you're going to calculate H beta line of Paschen. H beta line of Paschen. When do we get the Paschen series? When the electron makes a transition from higher energy state to shell number 3. Okay, since it is H beta line, so it is the second line of Paschen. First line of Paschen means 4 to 3. Second line of Paschen means 5 to 3. That means the electron currently is making a transition from shell number 5 to shell number 3. Right? Okay, you got to know exactly. I'm talking about H beta line. I'm talking about the second line of Paschen. See, in case of Paschen series, what is the low energy state? That is shell number 3. First line of Paschen, 4 to 3. Second line, 5 to 3, right? So you got the energy difference, right? You got the high energy state, you got the low energy state. You can calculate the lambda by using Rydberg's formula, as simple as that, right, people? Okay, so I'll be writing something. 1 divided by lambda will be equal to R. Z for hydrogen is 1. 1 upon N1 square minus 1 upon N2 square, right? Just solve it, get the answer, that's all. Right, people? So it's simply going to be 1 divided by lambda is equal to R. 25 minus 9 comes out to be 16. 16 divided by 9 multiplied by 25, correct? Or you can take the reciprocal, it's going to be 9 multiplied by 25 divided by 16 multiplied by 1 by R. 1 by R value is nothing, that's 911.5 angstroms. Just solve it. That's going to be the wavelength emitted during the second line of Paschen series. I'm sure it's clear to every single guy. You can just give me some clarity from the chat box if it is clear. Yeah? Just let me know in the chat box if every single thing is clear till here. Yeah? Exactly. Rydberg's formula is OP. Yeah, it's overpowered. Okay, clear to everyone. Perfect. This is one more question, guys. We can solve this question again on the base of same concept. We can solve the question again on the base of same concept. See, how do I approach to this sort of equation? See, guys, what this question says. What transition in the hydrogen spectrum? What transition in the hydrogen spectrum would have same wavelength as that of Balmer transition from, this is N, from N is equal to 4 to N is equal to 2 of HE positive spectrum. So on one side I'm writing hydrogen spectrum, on another side I'm writing HE positive spectrum, right? Hydrogen as well as HE positive both are single electron species, so you can use the Rydberg's formula properly, right? Okay, let's see how this question is to be solved. In case of HE positive spectrum, the electron is making a transition from shell number 4 to shell number 2. Okay, definitely when the electron will be making a transition from shell number 4 to shell number 2 in case of HE positive spectrum, it will be emitting some energy. It will be emitting some energy in the form of radiation. That radiation absolutely is going to have some wavelength, right? Let's say that wavelength I'm representing by lambda. Lambda is the wavelength emitted when the electron makes a transition from 4th shell to 2nd shell in case of HE positive. Yeah, in case of HE positive, right, people? I need to see what should be the transition in hydrogen spectrum such that the wavelength emitted over here is again lambda. So I need to see what should be the transition over here. What should be the transition over here such that the electron emits the same wavelength lambda in case of hydrogen spectrum as well. So what I'll be doing? I'll be again using the Rydberg's formula, okay? If I use the Rydberg's formula for hydrogen spectrum, I'll say 1 divided by lambda is equal to R. Z square value, that's 1. 1 upon N1 square, I'm writing as such. Minus 1 upon N2 square, I'm writing as such, right? This is the Rydberg's formula which I've used for hydrogen spectrum. Similarly, if I use the Rydberg's formula for HE positive spectrum, you will say 1 divided by lambda is equal to R. Z square, for helium Z value is 2, right? So 2 ka square comes out to be 4. Okay, 1 upon N1 square, which is 2 ka square, minus 1 upon N2 square, which is 4 ka square, right? Okay, so people, if you just solve it a bit, you will say 1 divided by lambda is equal to R. Just multiply this term by 4, this term by 4, what you'll be getting? You'll be getting 1 divided by 1 minus 1 divided by 4. Something you got it, right? if I want you guys to compare these two equations, what you can conclude from here? You can conclude one important thing. See, I can write it as 1 square. This 4 I can write as 2 square. This 4 I can write as 2 square, right? If I'll be comparing these two equations, you're clearly saying n1 value as 1, n2 value as 2, right? So, in case of hydrogen spectrum, when the electron makes a transition from 2 to 1, it will be emitting some wavelength lambda, right? Which is same as the wavelength emitted in case of HE positive spectrum when the electron makes a transition from 4 to 2 over here, right? I'm sure it's clear to everyone, yeah? Right, people? Let me know in the chat box if it is clear. Yeah? So, in case of hydrogen spectrum, when the electron makes a transition from 2 to 1, the wavelength emitted is going to be same as the wavelength emitted in case of HE positive spectrum when the electron makes a transition from 4 to 2 over here. Yeah? Perfect? That's great, Tanishq. That's great. You have done it earlier than me. That's wonderful. I liked it. Okay. Now comes one more point. How do we calculate the total maximum number of spectral lines when the electron makes a transition from higher energy state to lower energy state? What is meant by this? See, I'm writing over here calculation of maximum spectral lines. Calculation of maximum spectral lines. There is a formula to calculate it. First of all, what is meant by this? See, for example, this n is equal to 1. This is n is equal to, I'm talking about hydrogen, okay? This is, for example, n is equal to 3, and so on, okay? The electron is, for example, in n is equal to 3, and the electron has to reach to n is equal to 1, okay? Electron is currently, for example, in n is equal to 3. Now, it has to finally go to n is equal to 1, okay? So, how many possibilities are there for the electron currently which is in shell number 3 to reach to shell number 1? How many possibilities are there? One possibility is the electron will directly jump from 3 to 1, right? It will emit a wavelength. The second possibility is the electron will first jump into 2. After jumping into 2, the same electron will jump into first, okay? When the electron makes a transition from 3 to 1 directly, it will be emitting one spectral line. When it will be making a transition from 3 to 2, one more spectral line. From 2 to 1, one more spectral line. So how many spectral lines we got in total? We got 3 spectral lines in total. Yeah? Right? So how many possibilities are there for the electron to move from 3 to 1? There are 3 possibilities, right? There are 3 possibilities. Correct? But you're not going to do it in this way. This is the general concept, right? There's a simple formula to do it. Right? Let me give you that simple formula so that you can solve these sort of questions easily. Yeah? Maximum number of spectral lines is given by the formula n2 minus n1 multiplied by n2 minus n1 plus 1 divided by 2. This is the general formula to calculate maximum number of spectral lines when the electron makes a transition from higher energy state n2 to lower energy state n1. Right? Okay. Now people have a look. For example, in case of hydrogen, electron is making a transition from 6 to 1. So lower energy state, that is n1 is 1. Higher energy state, that is n2 is equal to 6. Put these values into this equation. Just kill it, right? So n2 value you are going to get as, you are going to write as 6. n1 value is 1. 6 minus 1 is 5. 5 multiplied by 6 is 30. 30 divided by 2 is 15. So total 15 spectral lines will be there, right? Total 15 spectral lines will be emitted when the electron makes a transition from 6 to 1, right? Now, one more case. Since the electron is making a transition from 6 to 1, so how many total spectral lines we get? We get total maximum of 15 spectral lines. If I'll ask you, out of these spectral lines, how many spectral lines will fall into the Lyman category? How many spectral lines will fall into Balmer category? How many will fall into Paschen category? How do we do that? There's a formula for that as well. What is that formula? See guys. Okay. or let me show it to you properly. See, this is the maximum spectral lines obtained, and this is the lines of spectral specific series. Lines of specific series. What do we mean by this? See, first of all, remember the equation. It's N2 minus ground state of that series. What is meant by this? See, let me make you understand this formula as well as this formula. Understand? The electron is making a transition from 5 to 1 in case of hydrogen. Let's calculate the maximum spectral lines first of all. So this is the value of N2. This is the value of N1, right? So N2 value is 5 minus 1 multiplied by 5 minus 1 plus 1 divided by 2. 5 minus 1 is 4, right? 4 5s are 20, 20 divided by 2 comes out to be 10. So maximum 10 spectral lines will be obtained, right? Now out of these 10 spectral lines, how many spectral lines will fall into Lyman, how many will fall into Balmer, Paschen, and so on? For that, you'll be using this formula. See, so let's assume I need to see out of these 10 spectral lines, I need to calculate the number of spectral lines which falls into Lyman category. It's going to be equal to N2, which is the higher energy state, which is 5 in this case, minus, what is the ground state of Lyman? Ground state of Lyman is 1. So 5 minus 1 comes out to be 4. So out of these 10 lines, there will be 4 lines which fall into Lyman series, right? Okay. Similarly, if I need to check out of these 10 lines, how many of these will fall into Balmer series? It's going to be equal to N2 right now is 5. What is the ground state of Balmer series? That's 2. So 5 minus 2 comes out to be 3. Right? So let's assume, let's calculate how many of these lines will fall into Paschen series. N2, that's 5. Ground state for Paschen is 3. 5 minus 3 comes out to be 2. 4, 3, 7, 2, 1. 4, 3, 7, 7, 2, 9. So one line is missing. Which is that? Let's check it. Lyman, Balmer, Paschen. Then comes the bracket. Right? N2 value is 5 for bracket. Lower energy state is 4. So the value comes out to be 1. Okay. So there will be, when the electron makes a transition from 5 to 1 in case of hydrogen, 4 Lyman series spectral lines will be obtained, 4 Balmer spectral lines will be obtained, 2 Paschen, and 1 bracket will be obtained, right? I'm sure it's clear to everyone. Yeah? I'm sure it's perfectly clear to everyone, right? No, Tanish, it won't go into negative. No, bro, no way. Okay? So let's try to solve few equations by means of which this concept will get clear. Yeah? Let's try to solve this question. Okay, let's try to solve this question, guys. A very simple one this is. See, hydrogen atom in the ground state, is excited by a monochromatic radiation of wavelength lambda. Okay. On coming back to the ground state, 15 different spectral lines were observed. Calculate lambda. So it's mentioned in the equation, hydrogen atom currently is in the ground state, N is equal to 1. So hydrogen currently is in ground state, right? The electron in the hydrogen is in the ground state, right? N is equal to 1. Now, this electron is absorbing some wavelength. It is absorbing some wavelength. After absorbing some wavelength, the same electron is going into higher energy state N2, for example. Let's say the electron went into higher energy state N2, correct? Since in the higher energy state, electron is highly unstable, so it will jump back. So when the electron jumps back from N2 to N1, how many different spectral lines are observed? There are some 15 spectral lines in total, which we get when the electron makes a transition from N2 to shell number 1. Okay. And how do we calculate the maximum spectral lines obtained, which is N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. This value is basically equal to what? This value is basically equal to 15, right? This value is equal to 15. Already N1 value we know, that's 1. So N2 minus 1 multiplied by N2 minus 1 plus 1 divided by 2 comes out to be 15, right? So this 1 got cancelled, so it becomes N2 square. N2 square minus N2 is equal to 30. So from here you got the quadratic equation. You got the quadratic equation right here, just a second. It is minus 30 is equal to 0. So after solving this quadratic equation, you'll be getting two values of N2. You'll be getting two values of N2. One value is going to be positive, one value is going to be negative. The positive value is going to be 6, right? The positive value is going to be 6. So basically, When the electron was at the ground state, after supplying some energy to this electron, it went to N2, and N2 is 6. N2 is 6. This is something which I got, right? So now the electron is making a transition from 6 to 1. I need to calculate lambda. So when the electron will be making a transition from 6 to 1, it will be emitting some radiation, which will be having the wavelength lambda, right? Okay. And the wavelength emitted by the electron when it makes a transition from 6 to 1, that will be same when the electron makes a transition from 1 to 6. Wavelength absorbed by the electron when it makes a transition from 1 to 6 is equal to wavelength emitted by the electron when it makes a transition from 6 to 1. As simple as that. Yeah. Let's check it out. I'll be using the Rydberg's formula again, which is going to be 1 divided by lambda is equal to R Z square. Since we are talking about hydrogen, Z is 1. 1 upon N1 square. N1 square is 1. N2 square. N2 square is 36, right? So from here, 1 divided by lambda is equal to R. 36 minus 1 comes out to be 35. It's going to be 36. Just take the reciprocal. After taking the reciprocal, you get lambda as 36 divided by 35 multiplied by 1 by R. 1 by R is nothing. That is 911.5 angstroms. This is the wavelength emitted when the electron makes a transition from 6 to 1, and at the same time, this is the wavelength absorbed when the electron makes a transition from 1 to 6. Yeah, I'm sure it's clear to everyone. Right, people? Right, perfect. So people are saying it is 937 angstroms. Yeah, maybe. Right? Okay, this is one more. This is one more for you. Give it a try. Give it a try, people. Give it a try. It's a simpler one, right? It's a simpler one, calculation based. Electron in the hydrogen atom jumps from some higher energy level N2 to third energy level. So N1 value is 3. So when it makes a transition from N2 to shell number 3, 6 spectral lines are possible. So maximum there are 6 spectral lines obtained. So 6 is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2, right? So you'll be getting 6 2s are 12 is equal to N2 minus N1. So it's going to be N2 minus 3 multiplied by N2 minus 3 plus 1 comes out to be minus 2. So it's going to be N2 minus 2, right? This value is equal to 13. You need to solve this. You'll be getting a quadratic right here, get the positive value, and that's going to be N2, which I was supposed to calculate. And N2 is basically the initial position of the electron, right? I need to calculate the initial position of the electron. The electron is making a transition from higher energy state to lower energy state 3. Higher energy state, which is the initial position of electron, N2, to lower energy state, N1, that is 3. Yeah, you can do it afterwards, I'm sure about it. Right, people? Right. Absolutely. Let's see if I have more questions. Okay, one more question. This is going to be our last question, right? And the rest of the things we'll be doing in the day after tomorrow session. Okay, perfect. But I want you guys, before ending the session, I want you guys to give it a try and let me know the answer of this question. I'll be giving you 1 minute. You guys solve it and let me know its answer. You guys solve it and let me know its answer fast. Give it a try. It's a very simple one. In a hydrogen-like atom, electron makes a transition from 4th excited state up to 2nd excited state. Okay, which option is correctly matched? Let me know. Yes, Krishnan, you can do it, bro. Okay, so people are saying option C, but there is not only a single option correct. There are more than one options correct. Let's get exactly how many options are correct. See, you need to be careful with the terminologies. In hydrogen atom, electron makes a transition from 4th excited state. He's not saying shell number 4. He is saying 4th excited state to 2nd excited state. 4th excited state to 2nd state. Be careful. 4th excited state to 2nd state. 4th excited state means shell number 5. Shell number 5. See, shell number 1 is called a ground state. Shell number 2 is called as 1st excited state. Shell number 3 is called as 2nd excited state. Shell number 4 is called as 3rd excited state. Shell number 5 is called as 4th excited state. 4th excited state is basically shell number 5, right? Up to 2nd state. 2nd state means simply N1 is 2. Low energy state is 2. So electron is making a transition from 5 to 2. So N2 you got, N1 you got. The question is done and dusted, right? See guys, I'll be writing something like this: maximum spectral lines obtained. Maximum spectral lines obtained, N2 minus N1. So 5 minus 2 multiplied by 5 minus 2 plus 1 divided by 2. This is the formula which I've told you. 5 minus 2 is 3, 5 minus 2 is 3, 3 plus 1 is 4, multiplied by 2, 4 3s are 12, 12 divided by 2 comes out to be 6. So total there are 6 spectral lines obtained. So 6 different spectral lines are obtained. So first one is absolutely incorrect, right? Now I'll be exactly checking out of these spectral lines which we got, how many of them belong to Balmer, how many of them belong to Paschen. How do we check that? There is a simple formula to check that. N2 minus, what is the ground state of Balmer? N2 minus, I'm writing it as ground state of that particular series. If I'm talking about Balmer series, I need to see out of these 6 spectral lines, how many among them belong to Balmer. N2, what is the value of N2? N2 value is 5. Ground state of Balmer is 2. So 5 minus 2 comes out to be 3. So out of these 6 lines, 3 of them will belong to Balmer, absolutely. And how many of them will belong to Paschen? So this is also correct. See, how many of them belong to Paschen? N2 value is 5. Ground state of Paschen is 3. So 5 minus 3 comes out to be 2. So this is again correct. So B, C and D, these are the correct answers among all, right? Okay. I'm sure it's clear to everyone. Yes, Krishna, exactly. Yeah? No, N1 is not 3. N1 is not 3. It is second state. He is not saying second excited state. If it was second excited state, then at that time I would have written N1 is equal to 3. But he is simply saying second state. Second state means N1 is equal to 2. Yeah? That's great, Roshni. Okay, so I'm sure everything is clear till here. So with this, your hydrogen spectrum is over, right, people? This is the question which I'm giving you as the homework. Do let me know the answer of this question in the comment section. This is going to be your homework question, guys, okay? It's a very simple one. Do give it a try. Let me know its answer in the comment section afterwards, yeah? So with this, people, I'll take a leave, but before taking a leave, there is something special which I would like to share with you. What is that? The batch for you guys for JEE 2023, the next batch for JEE 2023 is starting on 6th of September, right? 6th of September. What is the date today? I think today it was 6th of September, right? The batch started today. The batch has started today, guys, on the actual Vedantu platform. So you guys can be a part of it, right? I'm talking about the JEE 2023 people. You guys can be the part of it, right? Get trained by the super duper amazing master teachers of the Vedantu platform who teach on the actual Vedantu platform, right? Okay, so people, let me just give you the quick overview of how to get enrolled in this one. Well, there is a special offer which is currently going for you. See guys, we have got 3 plans for you. One is light, one is classic and one is plus, right? In the light plan, what do we have exactly? This is the 2-year classroom program and this is the course fee for complete 2 years. But no need to pay this much of amount in one go. Vedantu has kept EMI option for this as well. You can pay monthly in the form of EMIs, right? And if you are new to Vedantu, you have no idea how the actual Vedantu is all about. You can take this plan for a month, and for a month, right now, you are just going to pay this much of amount, right? After using the coupon code WBPRO or WSPRO, right? Okay, you can give it a try for a month. If you think you are getting benefited, absolutely you'll be getting benefited, right? Trust me on that. Just take the plan for a month, see if you are getting benefited. If you think you are getting benefited, then go for the 2-year classroom program, right? First, give it a try for a month at least, right? This is your light program in which you get live interactive online classes with the teachers of your choice in all the 3 subjects. Test series analysis will be there, note study materials, doubt solving during the class. All these things are in this light program. Similarly, we have got classic program. What all things we have got in classic program? Whatever things were there in light, apart from that, there is the doubt solving on mobile app, right? This again a 2-year classroom program, this much amount for the 2 years. You can pay this much amount in installments as well. If you are new to Vedantu, you can just use the coupon code WBPRO and get it for just 2K for a month. Give it a try for a month at least, right? Okay. Similarly, you have got the plus one. What all extra features we have here? You get the personal mentor in all the 3 subjects, and this is the course fee for a month, right? People, do check it out. Do check any one of these plans out. Whatever you think is convenient for you, do check it out and get enrolled, because the batch has started today. I want you guys to get enrolled in this one. Okay, the batch which has started today for the JEE 2023. right? And let me exactly show you how to get enrolled in this one. The ones who have not liked the video, please do like the video, share the video with your friends, and do subscribe to the channel as well. Okay, so people, let me exactly show you how to get enrolled in this one. See, this is the video which you guys are currently watching, right? This is the video which you guys are currently watching. You need to click on this show more. After clicking on the show more, you'll be getting a lot of links. Subscribe to Vedantu Pro, in which currently 50% off is going on. You need to click on this link. Yes, after clicking on this link, you can choose any of the plan. If you are going for light, classic or plus, light, classic or plus, any of the plan you can choose, right? Apply the coupon code WSPRU and try it for a month. After trying it for a month, I mean, you can give your number, your ID, whatever is convenient for you, okay? You can give it a try, get enrolled in this one. I'm sure it's definitely going to be beneficial for you. Do give it a try, people. The ones who have not liked the video, please do like the video, share the video with your friends, and do subscribe to the channel as well, okay? So I'll see you guys day after tomorrow then. Yeah? Yes, Akash, you can do that. 15 September से आप start कर सकते हो, right? You can do that. If you're not well currently, you can start from 15th of September, unless you get completely fine. Then you can start from the complete basics, right? From the mole concept, then atomic structure, then periodic classification, and so on, right? And if you have any sort of difficulty in understanding things, you can definitely ping me on over here on Instagram. This is my Instagram ID. You can just let me know, okay? I'll be letting you know what to do. Okay, with this, I'll leave people. See you tomorrow. Take care. Bye-bye. Thank you, Nandini.